All right, hey guys, this is the third video in the Chapter 8 hypothesis testing series. In the first video, which was part 1 of 8-1, we looked at the basics of hypothesis testing. Part 2, or 8, I'm sorry, 8-2 was the second video, which involves testing a claim about a proportion. This is the third video, which we're going to cover the claim about a mean. The fourth video is actually going to go back to section 8-1 part 2, which takes a look, a more in-depth look at the hypothesis testing procedure. All right, so one of the main things that we looked at in the prior videos was like an overview of a hypothesis test. And it involves three steps in general, right? Three parts. So the first part is making a claim about a parameter. And then the second thing is testing the claim. And then the third thing is we want to make a final conclusion addressing the claim and also addressing the null, because the null hypothesis is what we always assume to be true. So we first address the null by either rejecting it or fail to rejecting it. And then finally we address the claim. All right, and then the biggest part of this whole process, of a hypothesis test, is this middle part, the testing of the claim, right? It involves, first of all, identifying the null hypothesis and the alternative hypothesis, H naught, H0, and H1, right? And then the collecting of the sample is always usually given in the problem. And then we're going to perform like a p-value method or critical value method tests. We've talked about in prior videos the p-value method. We're going to still continue the p-value method. In the next video, we'll talk about the critical value method. So here in this video, we're still going to stick with the p-value method. And then we also looked at three functions for doing a lot of the calculations in the hypothesis test, right? We already looked at one prob z-test, which was for proportion. In this video, we're going to look at two other functions, the z-test and the t-test. And those two functions are for a hypothesis test for population mean. All right, so let's go ahead and get to it. These are some functions or some notations that you should be familiar with already. You've seen this, right? You've seen p-value, which is the probability value. You've seen alpha, which is the significance level, and these four for sure you've seen in other prior sections of the textbook. Okay, so let's go ahead and jump right into this problem. So the problem here says a group of students claim that the mean student loan debt at Fresno State is greater than 22,785, which is the mean student loan debt for California. The group randomly surveyed 36 recent Fresno State graduates. Those surveyed had a mean student loan debt of 26,337, and it is known that sigma, the population standard deviation, is 18,504. Use a 0.05 significance level to test the claim or to test their claim. Okay, so first step is we want to identify the claim in symbolic form. So in other words, identify the claim in math form. So the claim here is that the mean student loan debt at Fresno State, so for all Fresno State student, is greater than 22,785, which is like the average loan in California. And what the students are saying is that it's that the mean student loan debt, right, mu, the mean student loan debt for all Fresno State student is greater than that value. So the claim is that mu, the mean student loan debt for all Fresno State students, is greater than 22,785. And now we've got to test the claim, and that involves identifying the null and the alternative. The null hypothesis is always a statement that says there's no change or there's no difference in the parameter, right? In this case, there's no difference in the mean student loan debt. So in this case, the null says mu is equal to the 22,785, right? And then the alternative says there is a difference. And because in the claim we're stating that the difference is greater than 22,785, that's what we're going to have for the alternative. So mu is greater than 22,785. So the null we always assume to be true. it says there's no difference, no change. And then the alternative says there is a difference, there is a change. And this is what we're actually, collecting evidence or sampling to prove. If you didn't understand that explanation, I have here this table or this part right here. There should be another bullet point here. The null always has an equal sign. The alternative, these are the signs for the alternative, and it depends on what the claim is, what the sign in the claim is, right? So following this table and always knowing that the null hypothesis has an equal sign would always give you the correct symbol here. All right, so now we have to figure out the test statistic and the p-value. But before we get to that, I want to take a step back and I want to make sure you guys understand the whole situation. So we have our population, which is Fresno State students, and we're looking at their debt, right? We're interested in mu, which is the mean student loan debt for all Fresno State students. And there are thousands of Fresno State students currently, and thousands more who have graduated. So instead of surveying everyone, a sample was collected for recent grads, and in this sample, there were 36 students, and their average or their mean student loan debt of those 36 students is 26,337. Now, you might say, well, 26,337 in our sample, doesn't that prove what we're trying to claim? That the mean average student loan debt for Fresno State student is greater than 22,785? Isn't this greater than that? Well, we don't know for sure because this is only 36 students sampled out of thousands of people. We could have gotten this by luck. So what the test statistic and the p-value looks at is, well, what is the chances of getting this, or how extreme is this value, assuming that the null is true, assuming that we should get a mean of 22,785. How extreme is this, or what is the chances of getting that, right? So another way to think of it is if we have a mean that is farther away from or more or higher than the what we assume to be true, the more extreme it is, the more unlikely or the less of a chance of getting something like that. So this is clearly higher than that, but we want to look at, well, how extreme or how unlikely is it to get that value. All right, so to get the test statistics and the p-value, there are formulas to get that and procedures to get that, but we're going to use the TI-84 to get that instead, right? That's kind of like the easy way to go about it. So because this hypothesis test is involving a mean, we're going to either use a z-test or a t-test. So in this case, we're going to use the z-test because we know sigma, right? Sigma is given right here, 18,504. So we know we're going to use a z-test. So let me go ahead and show you guys what that looks like. So let me pull up the calculator. And we're going to go to stat, clear all this, go to stat, go to tests, and then z-test is the very first one. And we're going to do data, that's correct. And then mu0, mu naught is the value in the claim. So that's going to be 22,785. The standard deviation, the population standard deviation sigma is 18,504, and that's exactly what we have here. Ready? X bar, which is the sample mean, in this case, the sample mean is 26,337, and n is the sample size, which is 36. This next line is the alternative hypothesis, the sign in the alternative hypothesis or the alternative hypothesis, right? So the alternative hypothesis says the population mean, mu, is greater than this value here. So the population mean is greater than mu naught, which we defined as the value in the claim, right? Which is the same value in the null and the same value in the alternative. All right, so we're going to go down here and calculate. And we get that the test statistic is 1.15 and the p-value is 0.1247. So the test statistic is used in the critical value method, It's also used to find the p-value, like not using this, not using the calculator with the z-test, right? It's also used to find the p-value. I'll show you guys that in the next video. But for the p-value method, we're going to use the p-value. So if you guys recall, in the p-value method, we're going to compare the p-value to alpha, which is the significance level. So in other words, so let me kind of take a step back. The p-value tells us the probability of getting this result, assuming that the null is true. So the probability of getting the average, sample average or sample mean of 26,337 to 36 students, assuming that the average is true, the mean of 22,785 is true. So the probability is 0.1247. So is that a low enough probability to where we're going to say that this couldn't have happened by chance, right? This, getting this value, which is a lot more than this, probably didn't happen by chance. Well, to figure that out, to know whether it's low enough to where it's significant, we have to compare the p-value to alpha, which is a significance level. And if it's lower than, if the probability, the p-value, the probability of the result is lower than alpha, then we say, yeah, it's so low, it's much lower than our cutoff point alpha that it's significant, right? So in this case, it's not. It's greater than alpha. It's not, the probability of this result is not low enough to where we're going to say that, that this was significant or it probably didn't happen by chance. So we could have gotten this value by luck, right? So if you guys remember, when the p-value is low, we reject the null, right? So the p-value is, when the p-value is not low, then we don't reject the null. So in this case, because it's not low, we're going to fail to reject the null. So when the p-value is higher than the significance level, we fail to reject it. In other words, we're going to not necessarily support, but I'm going to put support in quotations. But in a way, we're kind of like leaning towards that. Hey, we're not going to reject this statement. We're going to lean towards this statement instead, that the average, the mean student loan debt is equal to 22,785, and we're not going to support the alternative. All right, so if you didn't understand that, just remember, refer to this chart right here. So when the p-value is less than alpha, we reject the null. When the p-value is greater than alpha, we fail to reject the null. So following that, you should be fine in getting the answer. So we fail to reject the null since the p-value is greater than the significance level alpha. And anytime we fail to reject the null, there is not sufficient evidence. So in other words, this value wasn't low enough to where we can say that there's sufficient evidence. So in other words, there's not sufficient evidence to support the claim that Fresno State students have loans greater than 22,785. All right, so hopefully that makes sense. Now, just while we're here, I wanted to just kind of make notes that there's two very important things that tells you that the p-value is largely depend on. The number one thing, or not, both equally important, but the first thing that it pays attention to is n. Like the bigger the sample, the more it's going to affect the p-value. And the second thing is the sample mean itself, right? So for example, let's say that this was our mean, which is higher than what we assume to be true, right? The 22,000. But instead of 36 students, let's say we sampled, I don't know, like 1,000 student. What's going to happen to the mean? I'm sorry, the p-value. So the p-value is probably going to be a lot lower because now we have more evidence, right? We have more students, and the average of the 1,000 students as opposed to 36 students was 26,337, right? So let's go ahead and change that. So temporarily, let's change that to 1,000, the 36 to 1,000, see what happens there. So we're going to go to stat, tests, z-tests, and we're going to change that 36 to 1,000. And you're going to notice that the result is that the p-value is going to shoot, it's going to go down, right? See how it went down? Again, this p-value, it's not 6.409. That p-value is a probability value. It's got to be between 0 and 1. So now why is it 6.409? Well, it's not, because there's, see this e to the negative 10? That's scientific notation for moving this decimal point 10 times to the left. So we move this decimal point 10 times to the left. This value right here is like 0.00009 zeros and then the 6. So that's a very low probability, right? So just kind of something to think about. Again, this p-value is dependent on these, largely dependent on the sample size and largely dependent on the actual sample mean that we get, right? The larger the sample size, it's as if we've collected more evidence, right? Our evidence is stronger, and then the higher this is, then it's like it's further away from what we expect, right? Okay, so let's go ahead and do another example. Um, so in this example, we have it's the bags of beans problem. Customers at a local farmers market complain that one of the merchant is being dishonest with the weight of beans labeled on their package. In a sample of 24 randomly selected bags of beans from the merchant, the mean weight was 4.8 pounds with a standard deviation of 0.68 pounds. At a 0.10 significance level, the farmer's claim, that the mean weight of his bags of beans is 5 pounds. All right, so the farmer here claims that the mean weight of all of his bags of beans, is 5 pounds. So it doesn't say like less than, it doesn't mean less than or greater than. Is means it's equal to, right? So equal to 5 pounds. So our claim is going to be mu is equal to 5 pounds. For the sake of just keeping it clean, I'm omitting the unit measured. The null says that there's no change or no difference. In this case, there's no change in his label and what the actual weight is. So mu is equal to 5. So take note how the claim and the null happens to agree in this, happens to be the same in this problem. In the prior example, the claim and the null, and then the alternative was the same. So again, the claim um, is not, don't assume like the claim is always the same as a null or the claim is always the same as the alternative. That's a common misconception or common misinterpretation a lot of students make. So don't always assume that. It does change. So the null always has an equal sign. So that's what we have there, right? And it also states that there's no change. The alternative always says that there is a change or a difference. In other words, in this case, it's a statement that says that there's a difference in the average weight or the mean weight of these packages and what's on the label. And it doesn't say whether it's less than or greater than. So if the problem doesn't specify, or if the claim doesn't specify that there's like less than or greater than, we just assume that it's not equal to 5. So if you didn't understand the explanation, again, I recommend just look using this chart right here, right? So the null always has the equal sign. The alternative, the sign of the alternative depends on what the claim is. So in this case, the claim, it was like a equal, so the alternative is a not equal, right? So in this case, the alternative is not equal. All right, now we got to find the test statistic, the critical values, and the p-value. So I'm actually going to save this critical value until the next video. Let's just go ahead and do the test statistic and the p-value. And for this, we know this is involving a mean. This is a hypothesis test involving a mean. And we know we're going to have to choose between z-test or t-test. So z-test is where sigma is known. Sigma, again, is the population standard deviation. And t-test is where sigma is unknown. Well, which one is it in this case? Well, let's see. We're given the mean, right? The mean here is for the 24 bags of beans, so this is x bar. We're given the standard deviation, but is this sigma? It is actually not sigma. So notice how the standard deviation here is for the 24 randomly selected bags of beans. So this is actually the sample standard deviation, S, lowercase s. So in this case, we're going to use t-test because sigma is unknown. Sigma, again, is the population standard deviation. This standard deviation is the sample standard deviation, which means sigma is unknown. We're not given sigma in this problem. All right, so let's go ahead and put it in the calculator. So we're going to go to stat, t-test, and mu naught, mu 0 is 5, right? It's always the value that's in the claim. X bar is the 4.8. S is 0.68. It's right here. N is our sample size, which is 24. And then the alternative, this is the alternative, has the not equal sign. So we're going to choose the not equal sign there. Press enter to select it and then calculate. So the test statistic, notice that it's a t-test because we're in the t-distribution. So the test statistic is a t. So t is approximately equal to negative 1.44. And the p-value is 0.1631. All right, so we're rounding to 4 decimal places. All right, so using the p-value method, so we're going to compare the p-value to alpha. So the p-value is 0.1631. So that's the probability of getting this result, right? The sample result of the mean of 4.8, assuming that the null is true. Assuming that the null is true, that we should expect a mean of 5, and then we got the 4.5 in the sample. This is the probability of getting that result, right? Getting this sample result. And now, is this probability low enough to where we can say that this getting this value that's different from 5 didn't happen by random chance? Well, how low is low enough, right? So again, we got to look at the sigma. So we got to compare to sigma. So sigma is sort of like our cutoff point. So this is not low enough because it's not lower than sigma. It's actually bigger than sigma. Not sigma, I'm sorry, alpha. Alpha is our significance level. So we failed to reject. So because it's not low enough, we failed to reject. Failed to reject, a weird way to, phrase this, but we're not rejecting it, which means we're kind of siding with it, right? We're leaning towards this statement as the evidence is kind of pointing to the evidence is kind of suggesting that we're not going to reject this. I'm going to put it in quotations as support. Technically, it's not always we're supporting it, but it's one way to think about it. And then we're either going to support it, or we're not supporting it, right? We're going to if we're going to support this statement, we're not supporting the other one, the alternative. All right, so we failed to reject the null since the p-value is greater than, right? Greater than the significance level alpha. Anytime we fail to reject, there is not sufficient evidence. So one way to look at it, this is not far enough. It's not far enough from what we expect to where we're going to say there's sufficient evidence, right? So there's not sufficient evidence to reject the farmer's claim. All right, so hopefully that helped a lot. If you have any questions, feel free to shoot me an email. Please watch the other 2 videos before watching this one. I should have mentioned that in the first place, in the beginning of the videos, but if you haven't watched it, please go back and watch those 2 videos. It makes a lot more sense when watching those 2 videos. And I'll see you guys in the next video.